So, how many of you work in language modeling or sequential modeling? Okay, not a huge number of people, but good to see some hands. So I apologize to those for some of the tutorial material in here, but I hope I can make it fresh for you too. But I think some of that will be necessary to fully appreciate the Brains guide here. Okay, I'd like to thank my own lab, the Brain-Inspired Computing Lab, notably Javier Turek and Dr. Vivo for their work in this project, as well as Professor Alex Huth and his students at UT Austin. What I want to talk about is how the brain can inform better language understanding, especially in particular in the space of how context is applied to derive understanding. So natural language understanding is a form of natural language processing that deals specifically with machine reading comprehension. So there's clearly a wider scope of NLP problems out there, but I'm going to talk about this one. An example would be this word problem. Please don't get nervous. I know that when we put up word problems, it brings up anxiety, but hopefully you can answer this one. It's not that difficult. Back in '64, they were trying to solve problems like this to get computers to answer those questions. Here's a little more difficult one. Don't worry if the answer doesn't come right away. But the idea was to take just raw input text and solve a reasoning problem embedded in the text, and so it could be stated any way that a human would naturally state it, but it should lead to a logical answer. Obviously, back then they were using things like the programming language Lisp to do some NLP processing on this to tokenize it and provide parts of speech and sort of turn the sentences into more canonical structure. The language understanding part comes after that and remains the tough part of the problem, and that is figuring out that Tom gets 162 out of this little deal. So what I'm interested in is not only the meaning of the words, the lexicon, how we use words in this type of context, but and their structure in sentences and so on, but the context, which is what it gives us a pointer to what the meaning of this particular pronoun is in this context. Obviously, a dog barks and tree bark. Context is important, and we think of it in a very local way, but you can easily read a novel and understand the context of a key sentence at the very end, and it'll strike you potentially very differently based on the rest of maybe even something that happened in chapter 1 of a 600-page novel. So that's way beyond what we see machines being able to do today. And it's really valuable stuff. I mean, we're seeing, obviously, language understanding has a role in machine translation if we do it right. It has a big, important role in question answering, especially when it comes to questions that are derived from background material, reading comprehension, longer form narratives like this out of the Stanford Squad 2.0 project. It can be even combined. You can combine sequential modeling with visual modeling and come up with visual question answering. But of course, look at the question. The question is in the form of a sequential statement. And finally, maybe more interesting and harder to reach would be answering general questions that draw on a huge knowledge graph of your whole understanding of the world around you, like this one out of the Allen Institute, where there's a general question about the population of mice, what would happen to it, but you have to understand this connection between these different things in the problem, and it's not stated directly in this question. There's no information given here. So that's kind of the holy grail. So, when we go to even longer form like this particular, narrative here, for us, we have to retain information across it, and that's key to our comprehension, as I mentioned. But we have to figure out, if we're going to do that, what the system is for representing it in terms of representation form. How do we internally represent that knowledge that we have externally on the page? How is it organized in our brains or in machines? And how is it effectively resurrected and applied at the right moment in problems? So the brain's already great at that, and so we're interested, I'm interested, my team's interested, and our collaborators in what it can teach us about this problem and how to solve it. And so the key questions I want to ask are, how does the brain organize and represent narratives? How well do deep learning models deal with narrative context today, the state-of-the-art models? And are the ones that are doing well, the state-of-the-art, are they more brain-like? Are they more brain-like? And I think that's the new part of the question. And then, of course, we want to turn these models back on the brain and see if they can help us inform better about the brain. I mean, machine learning has been unleashed on neuroimaging data, neural recordings, all kinds of neuroscience-related, cognitive science, psychological data. And machine learning is helping us better understand that difficult data. So those are the key questions for the talk. First one. How does the brain organize and represent narratives? Well, we're just scraping the surface on that. There's not a lot done on that. Alex Huth, our collaborator at UT Austin, has spent an extensive amount of time on this, has developed a number of semantic maps of the brain. And what you see on the right is a neuroimage of a brain. It's the brain activity actually measured through functional MRI that's picking up on the blood oxygen levels, which indicate the level of neural activity locally. And so these images are images of voxel spaces, three-dimensional pixels. And so we're looking for what lights up when different tasks are being performed or when people are doing self-supervision as they basically just read information, and as the brain goes about its job of predicting what it's going to read next to help inform its understanding. And so what we understand immediately from looking at this work over the last couple of years is that there's a clear hierarchy of different timescales. So convolutional neural networks came about from neuroscience as well, and it's not surprising that we're going back to the brain for this here. The hierarchy for a convolutional network is very clear. There's a spatial hierarchy, and there's a receptive field concept. And then there are different features that are understood to live in different layers of the network, going from very small features that, primitive features like edges and colors up to composed objects at the later layers. So that understanding, you can thank a lot of the visual cortex neuroscience for that. And so the question has been, is there a similar hierarchy in the auditory cortex and the language pathways of the brain? And so that's what this is about. So yes, the answer is it's not spatial. It's organized in terms of time scale. It's a multiple time scale. So you can see in the image here that we have different regions of the brain that light up. If we take a narrative and scramble it at different levels, we can study this. So we can scramble a narrative at the word level, the sentence level, the paragraph level. And by doing that, we can isolate what parts of the brains are actually able to process the information given that level of scrambling. So you can see very clear there's a different area that is focused on word meaning, sentence meaning, paragraph meaning, and so on, and the full story, right? And so that's one hint that there is a strong hierarchical organization. There are other questions like how do these regions connect to each other? What are the particular representations with them, and so on. But we do understand that as you can see here, a very clear pathway through where we would expect to see the language pathway in terms of mapping out the brain physically, anatomically, where the early stages of auditory processing you see are red and labeled 1 in there, deal with words and subsequent information in terms of just audition input. And then later stages are deriving meaning. Even across minutes and hours, we see more semantically related information in those areas. So, that's what we know about the organization at that level. And I'll come back to this, but this is enough for us to go ask some questions about these networks. And even though we know this about this multiple timescale architecture of the language pathway, we still know, as I mentioned, very little about the way the structure is connected throughout it and the format of representations within. So that search goes on, but there's some very good work toward that understanding. So the question is, for us to first determine what models of interest to look at and compare with the brain, we need to ask how well they do on these types of things. So let's take a short history through the recent models in sequential modeling. So first, there are recurrent neural networks and their variants. And then more recently, the temporal convolutional network. You may have come across that. I'll visit it and give you a short primer on it. And then finally, transformer networks, which seem to be really revolutionizing things right now, are like very much the state of the art. There's even a variant on that I'll talk about. So these are the ones of interest, and the question is again, how do these deal with context? And then later, are they doing it in a brain-like manner? So we have to have a objective way to evaluate them on these things, and it would be difficult to work directly on language understanding when in a more primitive task. So let's talk about sequence modeling in general. We're given a sequence input of symbols x0 through xt later in the sequence. It could be in time. We have a set of desired outputs or corresponding outputs that are predictions, and we wish to learn an approximation of what those outputs are. So we're learning a function that can map from the inputs to those predicted outputs accurately. And we want to put a constraint on that where our prediction about a particular output at time t is only dependent on inputs that came earlier and outputs potentially that came earlier in time. So it's causal. Okay, that's sequence modeling as generically stated as possible. And that is interesting here because when applied to language, it is language modeling, and language modeling in the strict sense of predicting the next character or word in a sequence, or et cetera, other parts of a narrative. And that's an interesting process, and it can serve as a backbone for NLP tasks of all sorts and language understanding. So we're really carving out a key part. It's self-supervised in that it's looking at its own information to make further prediction. We're looking at the input we previously had and so on. There's no other supervision on it. And it exploits context to make this prediction in a very pure way. So we'll use it as a proxy to study the underlying models that NLU solutions are being built on. All right, what would be the tasks that we would use of this sort? Well, we could do very simple primitive tasks. We can, but these have to involve things that would be challenging in terms of context. Now, context, I mean, how do things in the sequence influence other things that come later in the sequence and that span time or distance in the sequence itself, okay? So we don't want to just add two numbers. I mean, we can do that with other networks. We want to add two numbers that come out in a sequence and have a long delay between their outputs, and then maybe even delay the output of the addition to a later time and see if the network can hold things in memory and produce that output even later. So that would be an example of addition task. We just mark two numbers, say add these two, they're very far apart, and the farther apart they are, the harder the task is for the network. We can do the same thing with copying. We can ask it to copy a sequence that came way earlier and put a bunch of random stuff in between. We can ask it to classify, even using image sets where we just serialize the pixel values into a vector and then have it predict the digit number later. So it has to derive some information from the whole sequential pattern, which is very, and all the way back to 784 steps earlier. So that'd be a very challenging problem. And then maybe the ultimate would be to actually give the model as a sequence a whole book or a full narrative. And there are really great data sets for out there that have many, many passages in them. And that here's one that we're going to talk about later again. It uses almost 5 sentences with the context to do most of the predictions on average. So that's really interesting. Should be a good benchmark. So that's what I mean by sequential modeling and sequential modeling tasks and how we're going to benchmark these models and then decide if the ones that are better at it are more brain-like or not. So recurrent neural networks, the quick primer on it. So it's just a simple neural network that will make a prediction of the next step in a sequence by using a hidden state. And the hidden state is stored in terms of a weight matrix inside of this element. And it's just an encapsulation of all information about the sequence up till this time. So it's supposed to represent a summary of the sequence up to this time. So basically, we're learning a function. To do this accurate, we're learning a function of what is the hidden state at this time step and how should it change to the next time step given the current input. All right, and we just do that recursively, and we just keep doing it and doing it, and that's why it's a recurrent neural network. And so the new state, some parameters, the learned matrix W, the old state, and some input vector. That's the foundation of it. And we have to talk about these because they were the foundation for sequential models for so long. And they had become very effective through many changes. So thank you, Stanford's excellent course, Fei-Fei Li and team, for this good example. So this is how you would train such a model. There's an internal matrix, in this case a vector, the hidden layer. You put a character, one hot code of characters into this thing. The hidden layer and output layer matrices learn. The part of the matrix that does those two steps learns to transform that into the next character output. So in terms of using a softmax, for example, we could select the maximum probability of being, for example, an E. And we just put in a training sequence and update the matrix through a back propagation through time, just a variant of back propagation to do this task. And so at the end, it should be able to produce hello in this way. And we'll feed it a character like H, and it'll generate E, and then we feed the E back into the input, and that generates the next L, and so on. We keep going, feeding the output to the input again, and it will generate hello based on the prediction, just starting with an H. It should H-E-L-L-O. So that would be a very fundamental thing for a recurrent neural network to do. In terms of context, the problem with these is that they're very hard to train over long timescales. So the problem was recognized by many people, I think Hawkrider, Bengio, a long time ago, and it's called the vanishing exploding gradient problem. And the problem is that since you're using the same element to do the whole sequence processing, that updates of that weight metrics over time are propagating over and over and over and over. And if you look at the form of that weight matrix and look at its singular values, it turns out that if they're greater than 1, eventually the gradient will explode, and if they're less than 1, it will vanish. And so you can only, and the problem is that we're telling it to remember things over the sequence. We're trying to make this weight matrix preserve information over time as maximally as possible without exploding, and it's a very fine line. So that's a very tough thing to do with, since you see the gradient training pathway through backprop through time would be this red path through the model. It just keeps going through the same weight matrix over and over. It's the same one. So clever techniques were derived to stop and start and retain information flow through these networks. We call those gated RNNs. And basically you see an example there on the right where it's a very similar architecture, except that it has these gates that can stop the input, the output, the recirculation of information in the hidden state, and make the element forget as well by doing that. So that is what long short-term memory is. And you can see the more complicated architecture. So in exchange for being able to deal with longer contexts, we had to develop a model with more parameters like this and more complication. And it's not clear how brain-inspired this is at all. Although ironically, it was inspired by brain ideas that we have this ability to gate inputs and outputs and selectively retain information. So at a high level, there is brain inspiration there, but I'm not sure it looks just like that. So anyway, that solves part of the gradient problem. And you see that these were as revolutionary for a couple decades, a decade and a half, as CNNs were for spatial processing. And you can see an example of the performance in terms of the ability, the accuracy of prediction over the length of a context, the length of a sentence, for example. And so instead of being limited to like 10 or 20, you can get much better, you can get accuracy to 20, 30, 50, if you're lucky, with very careful handling. And so it solves many toy problems and real applications, and was used for, the early machine translation, natural machine translation, neural machine translation, and text-to-speech and all that. And if you just go a little further and not only do this type of backpropagation over time, but also over depth, and you stack these things on so that the hidden state is also updated by the previous layer as well as over time, then you get to some pretty sophisticated looking processing. For example, Andrej Karpathy did a bunch of work on this and has a great blog that you should go take a look at called The Unreasonable Effectiveness of Recurrent Neural Networks. Here it is learning to predict or produce basically Shakespeare's sonnets, and from a very simple 3-layer 512 node RNN. And so it starts in the training, it looks like that. And if you train it further, it starts to form words and breaks that make sense. Soon it's uttering things, and then now you can actually understand what it's saying, even if it's making up some of the things it's saying. So it will go where it goes in this prediction, but it looks a lot like Old English. So after a few hours of training, you can see it even has the larger structure figured out, with different rules and breaks in terms of the paragraph structure here. So I recommend reading that blog. It's a really great blog. So he applied it also to seeing if it could process LaTeX source code and produce what looked like algebraic geometry books. So that was, and see if it could learn other types of syntactic structure. So here's an example. It actually produced this page, which is pretty astounding. And it's total garbage math, but it looks very reusable, and it even says, look, proof, see the discussion of sheaves of sets. I mean, it's very, it can be a very clever network. So, but this also exposes some of the problems with it. So, for example, here's what the LaTeX code actually looks like that generates that kind of image, for example. And remember, we're interested in context and long-term dependencies. So in this case, what's missing here is obviously the proof is not ended, right? And then it ends some lemma that it never started. So, that's a problem. That's a long-term dependency problem, possibly. It forgot, what it had started. It never closes this begin enumerate. Same thing with code. Code's a great way to study whether it's getting long-term structure, right? So here's an example of, I think it was like the Linux kernel or something, and a larger RNN. So it correctly learns to use brackets, yay. Comments here and there. The kernel blank will, whatever that means, I don't know. Proper syntax for strings and pointers. But it often also does weird things like uses undefined variables. People do that too. And declares variables it never uses. People do that too. But more interesting for our talk, weird things like that. Another problem with long-term dependencies, it has a return where it doesn't need one, and so on. So definitely these are struggling. Even the best RNN work has struggled to capture long-term dependencies, although it's doing a pretty darn good job on the short and midterm. So now we advance to the state-of-the-art models, right? So these are the ones that are disrupting LSTMs today. We have the temporal convolutional neural network up first. So this is basically, for those that work in convolutional neural networks, a 1D fully connected convolutional network with a causal convolution. So it basically will look at a receptive field that only goes back in time, and it treats the input vector as a sequence in time. So you can see that there's an asymmetry in terms of the connectivity model here, instead of being the typical convolutional kernel that would have a receptive field to the left and right of center, right? So the other thing you probably notice, and by the way, the reason this was done is that I think the CNN people were frustrated with how bad the LSTMs were and thought we can go do this too. Why are those things so fickle, and why are they so limited? By the way, we can do any size receptive field, so we should be able to capture giant context if we want to by just increasing the number of layers and changing the kernel size. So also, we know CNNs are highly parallelizable. They run great on modern computer architectures. Like I said, you can independently determine the size of the context you want through the field size, stable gradients, et cetera, et cetera. So they're great. And in this particular, they try to take a very simple architecture and prove this out. One trick, by the way, to getting a very long history, because they do pay for very large input sizes on convolutions, is to use dilated convolutions. So you can see these convolutions are not looking at every adjacent input, right, they're skipping some. And so that's the dilation trick, where you're going to skip some neighbors and you widen the receptive field at the expense of resolution within the field itself. But you can see that it's kind of logarithmically increasing the field size. And so you can get a very large receptive field very quickly with very small amount of depth here, and very few parameters in the model. And so that's really cool. All right. So let's compare them with LSTMs. So that lambda task that I mentioned, a measure of perplexity here in terms of how well it's doing at this model prediction, sequential modeling task. Lower is better here, and the TCN blows away the competition. GRUs and LSTMs are just a variant of one another. One's missing an output gate, the GRU. The RN is that vanilla one that I explained to you, but it's by far exceeding those on these tasks, and probably because it can handle the larger context. At least that's the arguments in the papers. It can handle the larger test contexts, and it's more computationally efficient. In fact, here's some direct evidence. I mean, if you compare the TCN with the others, I mean, the test accuracy does not drop as the sequence length that it's being tested on is increased. And yet that happens pretty drastically with the LSTMs and the GRUs here. So they're really not. They've dropped their accuracy quite a bit by as you get into the 100+ sequence length, whereas the TCN keeps trucking along. Who knows where it'll stop? So the charge that the CNN folks would level is that the unlimited, quote unquote, unlimited memory of LSTMs is bull. It's quite limited compared to the expansive receptive field of the generic TCN. It's pretty good evidence for that. But then along came transformer networks, the last class we'll take a look at. So transformer networks. Now, it's interesting, all three of these networks come about it completely differently. It'll be amazing if they're all actually following brain inspiration and organized like the brain, but maybe they are. We looked at the CNN approach, we looked at a sequential modeling approach with recurrence, and now we're looking at an attentional model that has absolutely none of the previous two. And the idea here is that all that matters is you're given a sequence and you want to scan it for the areas to attend to make the best prediction later. So it's all about where you allocate attention. In this case, we're talking soft attention. We're basically putting a weight on the importance of information to the current prediction. And we're doing that through a simple dot product trick where we take generically what we call a query, which is information that we're looking for, and we're looking for the more similar that is to a representation or a key that we have, and the more similar they are, and to the value, it's content addressable. That's the attention, that's where we'll put the attention, and we'll put a weight on what that representation is driving us toward, and less on the ones that have a smaller weight. So this is the attentional model, and you can see their architecture on the right here. There's a encoder, which is encoding the input sequence, and then it forms an internal representation using the attentional model, and then that is fed to a decoder, which generates the output sequence and puts it back into the sequence space from the internal representation. And in terms of, this is all about attention, it has low computational complexity. You can determine the number of attentional spaces that you want to deploy. We call these the number of heads that you deploy. It's highly parallelizable because they can operate independently and be processed independently in terms of dot product, matrix multiplications and so on. And I'll get to this last characteristic, which is really important to context, which is the low path length between long-term dependencies. So I talked about the encoder-decoder structure, but I bolded the multi-headed part of this. So there are heads that allow us to attend to multiple parts of the previous, the historical sequence at different parts in the model as well. So the encoder has self-attention, and each encoding layer can look at parts of the previous encoding layer with the attentional model. In the decoder can attend to selectively to different positions from the input sequence, which are really the output of the encoder part of the model, and apply self-attention that's masked for causality, so it's not looking at outputs that it hasn't generated or parts of the sequence that haven't come yet, but it can look at any part of it, the output that it's already generated. And so this is where attention's applied, and that plus a simple fully connected feed-forward network allows this thing to do its magic. No recurrence, no convolutional. So, by the way, they have to inject positional encodings, and they do that through a sine wave signal that they inject into the inputs and the outputs so that they have an encoding of where the position is for each part of the sequence. There's no inherent position. There's no field. Okay, so why would you do this? Why would this make sense? Well, when you look at the math behind it, if you just look at the big O notation of it, the complexity, like I said, is quite low. If you look at it, it looks like it's similar to convolutional recurrent, but that dimension D is much smaller, much larger. That's the representation model dimension is much larger than the N sequence dimension most of the time, unless you get to very, very long sequences. So that's one thing that buys the self-attention something, because it doesn't have a squared term on D. The other thing is that all the other ones are O1, but the recurrent model pays for the sequential operations, has to do N operations to get a prediction forward in the sequence or to find a relationship. But most importantly to the context, it's not only the length of context that matters, it's the ease by which it can be accessed. So when trying to find relationships between distant parts of a narrative, you have to ask yourself, how many nonlinearities and matrix multiplications does that have to go through? And if you look at the architecture, it's O1 for the self-attention model. It can directly connect any part of it through the attentional head. The recurrent model has that n-sequence recurrence, and then you can look at the dilated convolution and derive the log base k n rule very easily by looking at the number of layers that it has to go through to connect two pathways in the input receptive field. Does that make sense? So they would argue, and I don't think this has been empirically studied enough, but that is why a self-attention model can reach into the past at any point and quickly derive relevance to the current point in sequential modeling more efficiently with less training. All right, so let's compare transformers versus TCNs. So we know TCNs are better than LSTMs. If we look at the great work by both the Facebook and Google teams on this, their blue scores, where higher is better, are lower than that of the transformer, both a base model and a larger version of it they made. And you can also see that the training cost is comparatively efficient for the transformer. So it's living up to its credit there. But also note that it does this with limited context. I didn't say that the transformer is going to look over a huge sequence. It's just doing an effective attentional model over only a 128 link sequence. Some of these other models had much larger input sequence sizes. And then if you look at the TCN model itself, this work by and compare it, you can see that the perplexity number lower is better is much, much better for this newer model called Transformer XL, which did away with the limited input sequence size and added a recurrence relationships into the model so that it could look at it could have an potentially unlimited history to attend to. So it basically does caches the old sequence learning for the next sequence learning step and can look back. And Wikitext 103 is one of the most difficult word level prediction sequence modeling tasks out there, and it does a great job on that. So in fact, you can see that in terms of context that so they measured the amount of improvement in score by adding more context to these different models. So this is comparing with an LSTM and RNN against that Transformer XL. And the Transformer XL is clearly getting a lot more performance improvement by adding even longer contexts beyond the LSTM. I don't know why it's not compared with the TCN here. And here's evidence, just looking qualitatively at it, that it's actually deriving long distance relationships. So it's being asked to generate these wiki pages, right? And some of this is hallucination. But the question is whether it's being consistent with its hallucination. So here you can see that it's talking about this player. I think it's a baseball player, and it goes from 2011 to 2012 to 2013. I'm highlighting it in red. So it's got that. It's remembering where it is in this whole task in terms of that. Well, it's doing all this other generation. And it even realizes the guy previously had an injury and saying that now he's had another back injury, right? And it's even, he never played for the Royals, so it's also generalizing well and making up stories. So, okay. So the question is, are the more effective ones like the transformers more brain-like or not? And so and I want to address at the same time because we're running out of time, whether these models can tell us anything more about the brain structure, because they are interrelated. So the question really is, are deep neural networks organized by timescale? So this is what we're talking about, right? If we go deeper into the model, is it considering a longer timescale? Is it dealing with higher level representations at the same time, like the brain does? The methodology to look at that question is an encoding model. And we basically just have people listen to, just read stories while they're in a scanner, and we can, from that, watch their predictive models as they work away, and we get neural activations from that over time, right, as they're reading that. And we've correlated the input to the neural activation space, so we're coming up with these multivariate patterns. And then we can do the same thing with an artificial neural network, just do some self-supervised training, just have it predict the same sequence, and we collect its unit activations. And then we apply a simple ridge regression model to see if the unit activations at different layers in the model are predictive of these voxels in the brain space, the activation space. Which of these models, we didn't train them on the task, in any way other than trying to predict the same thing we think humans are doing when they just read. Are the activations or the representations that are stored predictive of the representations we see in the brain? So there's evidence this would probably work. It's been done with image data and convolutional nets. It's been done with auditory, music, and speech processing, and it has done a great job for neuroscience in that way. Here's what we see when we look at it. So an embedding model doesn't use context. An embedding model is the comparison here. So like word-to-vec, that's just saying how similar are these words to other words in the embedding space. There's no context here. It doesn't take the narrative into account. So if the model's doing a great job of using context the way a human does, we'll see more color on here. You don't see a lot of color in the LSTM, right? You just don't see it. It's not doing better than an embedding model. It's not using a lot. It's not recruiting a lot of context. It's not predicting basically in the way, it doesn't have representations that are brain-like. The transformer is a completely different story. You can see that where red means is the big difference between the performance of the explained variance by the transformer versus the embedding model. And so you can see that just globally, it's a better model. It has more of a likeness to the brain. So also, if we look at whether certain layers in a multi-layer LSTM correlate to parts of the brain, white means no, and the answer is pretty much no. We can't map an LSTM layer to a part of the language pathway, whether it's low-level processing region or the higher-level semantic region. So open questions are, why do they do so poorly? They're not all that predictive of the brain. They don't exhibit layer-specific correlations. And do TCNs and transformers exhibit these multi-scale timescale characteristics? Yeah, they do. You can actually see if you correlate the early and late layers of the model with the pathway in the brain, you can see clearly it starts blue here and goes more red that way, and that would follow the language pathway. So there is a correlation between the representations and where they're stored in both the transformer network and the brain. And more interestingly, if you look at the correlation between where context length is processed and the layer in the model, we can see a very clear correlation between the map of where context is stored in the brain and where context is stored in the model. So we're showing that it's layer-specific, laid out layer-specifically. It's also laid out by context length. So that would be our case for multi-timescale there. And then you can look at the performance of what parts of the transformer model, what layers best explain the brain variance, the variance in the brain activity. And the answer is that the layers like around 9 later in the model best explain the full variance. So that makes sense. We're capturing all the context. But there's a drop-off as we go to layers 10, 11, 12, and that's a mystery. And it may be because the transformer and other models are trained to a specific task on the final layers, and we're looking more for the representations that are internal. And so the way we're adapting them for the actual prediction is different than brain, but the internal representations up to layer 9 are very similar. Now, that would explain this. So this was for 3 subjects that were compared, 3 human subjects compared with it, and a few other points I don't have time to go through. Sorry. But, oh, by the way, the temporal convolutional networks show a similar characteristic. So challenges and summary. So we know that the brain's language pathway is organized in a multi-timescale hierarchy, and that makes it very effective at utilizing context. Language models seem to be catching up with that. So this is all work that was published in the last 2 or 3 years. So that's amazing that it's gone from like dark on the brain to bright red, like literally, right? And Transformer XL looks like it's the, we studied the Transformer, not the XL, but I would suspect that that's even doing a better job of explaining brain activity. And so both the TCNs and Transformers have explicit multi-timescale hierarchies. You should be happy about that because that means these models are what they represent is maybe closer to here, being here and staying here, because we are using this as the ultimate inspiration for this whole line of work in industry, right? And these look pretty plausible. So, but we still have these other mysteries. Why are the last layers have lower predictive performance? How do we get more out of context at larger timescales? All of these drop off after a certain length that's much lower than what you could handle. And finally, why do RNNs and LSTMs just not work at all? Why are they, even though they have depth and you can have multi-layered models, why are they not capturing any sort of hierarchy like this, like the other models are? And if you're interested in what we've found out so far about how a deep RNN may be equivalent to just delaying RNNs and so on, and why there may not be as much depth to these models to begin with, go look at our paper on arXiv on that subject. All right. So I didn't say a lot about representations. There's a lot more that we need to understand about that, like what specific information is captured across the brain in terms of representations. There's some evidence of what's in the semantic spaces and so on, but a lot more needs to be done. And we don't know if the same precise representations are captured in these deep learning architectures, and that's something that we're studying right now. So I hope to give an update on that in the near future. And by the way, if you're going to NeurIPS, we have a workshop on context and compositionality there. We're going to look at this. We're bringing in some great speakers. Hope you can make it if you're there. I'm sure we'll have a packed room, so hope to see you there. Thanks.